So I want to look at some more equations, right? Ones that are a little different. These aren't quite as just take the inverse and you're done, as the ones we saw before. So first, one difference here, you notice I've put a restriction here, right? So I only want the answers that are between those two values. Right, so let's see how this is going to work out, because you notice there's another difference here. Instead of just being sine of theta, I have the sine of 2 theta. All right, but look, it's gonna follow the same process. Take the inverse sine of both sides. 2 theta equals the inverse sine of negative 1/2. All right, which means 2 theta equals, all right, so let's think about this. Inverse sine of negative 1/2. We're talking about third and fourth quadrant angles here. Right, so let's see, my first one in the third quadrant, the sine of 7 pi over 6 is negative 1/2 plus the usual 2k pi. And if we go over into the third quadrant, into the fourth quadrant, then the sine of 11 pi over 6 plus 2k pi is also negative 1/2. All right, so now look, divide both sides by 2, right? Just like we would normally do. Divide both sides by 2, and I get theta equals, now when I divide by 2, let me kind of write it in here. I have to divide everything by 2, including the 2k pi. So this becomes theta equals 7 pi over 12 plus k pi, comma 11 pi over 12 plus k pi. And now what I need to do is I need to just put numbers in there for k. I'm going to put 0, 1, 2, 3, and I'm going to keep generating numbers until I get up to 2 pi, and at that point I'm going to stop. Right, now there's going to be obviously fractions and such going on here. These work out easier if you go ahead and combine the fractions now, right? So I'm going to say, look, k pi over 12, this is 12k pi over 12, and this is 12k pi over 12. I'm doing a common denominator. So this becomes 7 pi plus 12k pi over 12, and 11 pi plus 12k pi over 12. Now, put numbers in there for k, right? If I let k be 0, theta is the original 7 pi over 12 and 11 pi over 12. Good. Those are both still less than 2 pi. Remember, when we're talking about 12, 2 pi equals 24 pi over 12. So when the numerator gets up to 24, that's when I'm going to stop. All right, so if I put 1 in there for k, I get 7 pi plus 12 pi. Oh, don't want to start again. I just continue my list. That's 19 pi over 12. And if I put 1 into the second one, the 11 pi one, that's 11 pi plus 12 pi. That's 23 pi over 12. And that's where I'm going to stop. You can go again. Well, let's think it through. Right? If I let k be 2, then this one becomes 7 pi plus 24 pi. That's 31 pi, which is too big. Right? So that's where I'm going to stop. These 4 angles are my answer. Okay, so how about this one? Right now I've got squares going on in here, right? Well, look, if you look at this, it kind of looks like a quadratic equation, right? In fact, if you really want to see it, let's replace cosine theta with x. All right, then this becomes 2x squared minus 3x plus 1 equals 0, and that factors. This is 2x minus 1 times x minus 1. All right, now let's put the cosine theta back. This is 2 cosine theta minus 1 times cosine theta minus 1 equals 0. And do what you always do when you've got something factored. Set the factors equal to 0. 2 cosine theta minus 1 equals 0. And cosine theta minus 1 equals 0. All right, so the second one I think is easier. This is cosine theta equals 1. So theta is the inverse cosine of 1, which is, okay, you might be tempted to say 0, right? But look, theta can't be 0. Theta has to be strictly greater than 0. It can, however, equal 2 pi. And the cosine of 2 pi is 1. All right, so now let's do the other one. Cosine theta, 2 cosine theta equals 1. Cosine theta equals 1/2. Theta equals the inverse cosine of 1/2. So what is theta? Theta is going to be pi over 6. And pi over 6? No, I always mix that one up. Pi over 3 and 2. Whoops, sorry, not 2 pi over 3. I need to go down into the fourth quadrant because that's the other quadrant where the cosine is positive. All right, so let's see. Pi, 2 pi, 3 pi. How about 4 pi? It's going to be 4 pi over 3. Pi over 3. 2 pi, 3, 4, 5. Yes, 5 pi. Thinking through my trig values in my head. 5 pi over 3. And there's my answer, right? Because I was limited to between 0 and 2 pi, I'm not going to do the 2k pi thing, right? Because that would take me outside of that restricted interval. Okay, so how about this one? Okay, I've got a mixture now. I've got sines and cosines, and that's rarely a good thing. Okay, usually life is really easier if I can have just one trig function in here. So here's what I'm going to do. I'm going to get rid of that cosine squared. Remember, we have our Pythagorean identity. Cosine squared plus sine squared equals 1, which means cosine squared is 1 minus sine squared. All right, so let's put that in here. 2 times 1 minus sine squared theta equals 3 minus 3 sine theta. And it's starting to look like a quadratic one again. So this is 2 minus 2 sine squared equals 3 minus 3 sine theta. All right, so let's set this equal to 0. I'm going to move everything over to the right. Right? Move the sine squared over and the 2 over. So if I subtract 2, 0 equals 1 minus 3 sine theta plus 2 sine squared theta. And now let me rearrange that. You always put the squared one in front. 2 sine squared theta minus 3 sine theta plus 1 equals 0. Now, we really can factor this directly. I did that switch to x thing just so you could really see the quadratic equation. But look, I'm going to factor this just the way it is. This is 2 sine theta minus 1 sine theta plus 1 equals 0. So I get 2 now, right? I get this factor gives me sine theta equals 1/2. And this one gives me sine theta equals -1. Okay, the sine is -1 when theta is 3 pi over 2. And the sine is 1/2. Let's see, that's first and second quadrant. So this is going to be pi over 6 and 5 pi over 6. And there's my answers, right? Because again, I had this restriction, so that's why I did not do the plus 2k pi thing. Okay, so how about this one? Well, let's see. Let's start by solving this for the cosecant, right? Get that by itself. Subtract 5 from both sides. 2 cosecant theta equals -2, which means cosecant theta equals -1. Now, maybe you can go right to the answer from here. Maybe you know what angles have a cosecant of -1. If you do, that's great. Awesome, you're done. Okay? Another way you can approach this, right? We're almost always, everybody's more familiar with the sines and cosines. So let's rewrite it that way. Let's make this 1 over sine theta equals -1. Flip both sides over. Sine theta equals 1 over -1, which is just -1. And then take the inverse sine of both sides. Theta equals the inverse sine of -1. All right, where is the sine -1? Sine is -1 at 3 pi over 2. And that's the only place, right, between 0 and 2 pi in kind of that first period that we look at. That's the only place where it's -1. So I'm going to add 2k pi onto the end here because there was no restriction this time. And those are going to be my answers. Okay, so we've seen several new techniques, right? We've seen how we can use trig identities to simplify an equation. We've seen how we can factor an equation and use, the factoring techniques and the zero product rule that we're already familiar with to solve equations. In the next couple of lectures, we're going to look at something called verifying trigonometric identities. Trigonometry has more formulas than you can shake a stick at. And we're going to look at ways that we can, if we're given an identity or a formula, we can verify that it really is correct.